online learning lecture. And we'll draw a connection between boosting and online learning. Okay. So we're going to give an online learning design for problems where the underlying concept is potentially changing over time. It's an extension of this experts algorithm, which we did already. We could further generalize it to winnow. It's a trade-off between warmth and noise. If it gets too hot, please let me know, but I need to hear myself think. Okay. Let's recall this online learning setup that we looked at before. This online learning setup we looked at before was the following. We were given a set of experts, and our aim was to do not much worse than the best experts. So the model was, here are our experts. We get here are our experts. They make predictions. After they make a prediction, the algorithm makes a prediction. We receive a label, which is feedback. We incur some loss, and our goal is to minimize the total square loss. So the loss of our algorithm was just the sum of the loss of the predictions of our algorithm. The loss of a given expert, if I was the best expert, would be the sum of its losses on the individual trial. We prove bounds to the form that the loss of the algorithm is less than or equal to loss of any expert I plus the best expert plus some term which depended on log n. Okay. Before I go directly into this algorithm, I kind of want to make a slight, quick, easy connection to boosting, which I won't go into a deep way. But if we try to perhaps compare this to boosting, what would be the story? The story would be that our experts correspond to examples. Okay, so we have examples 1 through n. On each trial, rather than nature giving us an outcome vector, we instead give a weak hypothesis. Okay. Then we go ahead and we reweight the experts, or we reweight the examples. In the experts algorithm, we reweighted them e to the negative loss, but now we do the opposite. We do e to the positive loss. So there's a kind of duality between the experts setup and the boosting setup. Go into some of those references, not the Hastings-Tishbarani, but either the Shapir or the Freund-Shapir reference. They'll bring this out a little bit more. Okay. We want to do something different. So we know what we get predictions. We make a prediction in 0, 1. We receive an outcome. We incur a loss. We have this normalized loss expert update according to the loss. We went ahead and improved the bound when this was mistakes. This was boosting. Here we imagine some loss vector, except we would be exponentiating it. It would be a negative there. Okay, so previously we discussed this bound. We showed how to get a slightly weaker bound for misclassification, where there was some constant in front of loss I and a constant in front of log n. But if we're really interested in online learning, like if we're interested in something that's changing over time, our comparator should change over time. I.e., we don't we don't want to have this IID type assumption. We don't want to believe that our examples are always coming from one place and never changing. You know, if we want to really predict online, a more natural assumption is that whatever the thing is which is generating our examples, it's not IID. So if it's not IID, we want some comparator, which isn't to do as well as the best object that we can fit on the whole sequence. Rather, we might aim to try to fit as well as the best sequence of comparators, and that's what we'll do. So to define the loss of a sequence of comparators where each comparator is an expert, it'll just be the sum of the losses on each of the segments. Obviously, to make the problem interesting, we want an algorithm to do well over any sequence of experts, but we're not going to tell the algorithm, oh, it's a new sequence you should use, a new comparator you should use. Okay. At a high level, the problem that's going to happen with these algorithms is that using this exponential weighting scheme, when we have lots of loss, the weights are going to get very small. So different ways of getting around this problem. Kind of what we're doing today is our weights kind of act like quasi-probabilities, and our algorithm will kind of treat things as if they're quasi-probabilities. Okay. So previously, we gave a bound in terms of the best single expert. We want to do well when things are changing. So now we define the loss with respect to a sequence of experts. So perhaps we have our L trials, and first we want to do well if our first expert is maybe that one, then that one, and so forth. So the loss of the sequence is just the sum of each given expert along that sequence. So to give an example, without plugging in the exact numbers, it's not hard to persuade yourself that expert 4 is the best single expert, i.e., you know, if it gets label on the first trial completely right, it's pretty near on the second trial, not so bad on trials 3 and 4. But if we're trying to do as well as a sequence of experts, for instance, we try to do as well as the sequence of experts with at most one shift, you can persuade yourself that, well, if we consider sequences with up to one shift, this expert doing expert 2 for the first 2 trials, then experts 1 for the last 2 trials has even smaller squared loss. So our aim is to show that we won't do much worse than the best sequence. Questions about the setup? Okay. How can we do this? I guess for those who are taking evolutionary computation, it's maybe a bit familiar now. But I want to make sure it's doing sequence. Okay. So previously, we proved an algorithm that basically said we could do well where we only paid logarithmically the number of experts. So one thing which we can do instead is, well, maybe we can define some sort of meta-experts which then do well. What do I mean? So suppose we have 3 basic experts: blue, purple, green. Let's make it 4. Now we know we can do as well as the best best single expert. But if we want to do as well as a sequence of experts, what we can do is kind of expand our set of experts, where we'll have some expert which corresponds to predicting like red for a while, then predicting like green for a while, then predicting like purple for a while, or maybe green for a while, then red, then green. I.e., let's say we wanted to do as well as the best expert which switches 2 times. Well, then we might have a set of experts where first we're red, then we're blue, and then we're green. Then we're red, then we're blue, then we're red, and so forth. We can consider all possible meta-experts which come from taking this sequence apart. Okay? So suppose K was 2, how many possible of these experts would we have? Well, there would be n minus 1 potential experts for the first segment. N potential experts for the first segment. For switching, we switch to n minus 1 experts. And if we switch again, we switch to another n minus 1 experts. How many potential places can we switch? Well, you could switch here and here, there and there, and so forth. We have, if our sequence is of length L, we have roughly L choose K switch points, and we had n times n minus 1 to the K switches. So what we do is we take our original set of experts, create a set of meta-experts of which there's L choose K n times n minus 1 to the K meta-experts. So then if we go ahead and plug this into this bound over here, we know we do as well as the best meta-expert plus K log n, well that's roughly this term, K log n. Then we do the log of L choose K, which is roughly K times log L over K, i.e. log of this is approximately K log L over K plus K log n minus 1 plus log n. Okay? Questions how this construction works. So it's an idea of how to build a construction, but problem with this as an algorithm is that if we have to create all these meta-experts whose weights we keep track of, we need to combine. Well, we created L choose K times n to the n choose K. It's clearly exponential in K. A weaker problem we might be concerned about is we have a bound that grows logarithmically in the length of the sequence. Okay. Questions?
This is online learning, so you'd have to be keeping, if you're following that, you'd be keeping all of those exponential number meta experts going, and they'd increase by every time you got an extra.
Well, this is maybe assuming that somebody told you L in advance,
okay.
But you could also increase it as you went along the way, and you keep growing this. You know, it'd be very painful.
Yes.
We wouldn't want to run this algorithm for very long. But where we're going is we want to show that this kind of gave us an idea where to go, but we actually don't need to do this to get a good bound. But this is a general trick that people use, not just in online learning, all over the places, is they think about, well, how can I solve my algorithm by simulating some very complicated combinatorial explosion of small algorithms, and then see if I can then do it efficiently. There's many things that we could do in machine learning if we could run algorithms that take exponential time. Only some cases, this being one of those cases, can we get things down back to something efficient. Okay. Kind of complicated. We'll explain things graphically in a moment, and we'll explain where at least one of these updates comes from. Okay, so what I'm going to do now is propose two solutions. It turns out that actually we can do quite well and prove a bound in terms of the best sequence of experts by simply changing our update strategy slightly. Okay? So we do what we've always done before. We create new weights by taking e to the minus loss so far, and then as desired we could normalize at that step, or we can normalize later on. It doesn't matter when you normalize. Once we've done the loss update, we're going to show that you can do well fast. Two updates. We're going to forget about the second update, and we'll focus on the first update. But basically, what we're going to do is every given expert is going to share a fraction of its weight alpha, and we'll put all the weights shared into a pool, and then every expert, it's shared one fraction of its weight alpha, so it keeps 1 minus alpha of its weight. The rest got put into this pool. From this pool, every expert gets back a uniform proportion of weight in the pool minus its own contribution. So we kind of redistribute the weight. Graphically, to think about what's going on, we're doing the following. We have our n experts. We do the loss update. Then after we do the loss update, each expert has its weight. It keeps 1 minus alpha of it, goes back to itself, and then it gives off alpha n minus 1 of its weight to everybody else. And that happens simultaneously for all n experts. Okay. So we can go ahead and that algorithm we can then bound. So somehow we said we're going to do as well as the best sequence of experts. It's probably unreasonable to expect us to allow us to switch every single trial and do well. Okay, somehow we want to do well with a moderate number of switches. So like everything else that we've done so far, we'll kind of assign a complexity or a size to a sequence of experts, and that size will be just the number of switches. So if we switch once, k is 1. If we switch twice, k is 2. Imagine if you're doing linear classifiers, maybe you have a sequence of linear classifiers, and you want to do as well as a sequence of linear classifiers, then maybe you want some smooth measure of switching between linear classifiers. If the linear classifiers have similar representations, maybe this should be small. Okay, so the loss is just a sequence. As you saw before the algorithm, we introduced a parameter alpha. Let's ignore this first bound. This is one kind of very clean way of writing the bound for this algorithm. We can write the bound in perhaps a less clean fashion, but easier, more intuitive to understand format as following. So we get something quite similar to what we got before. We get the loss of our algorithm is the loss of any given partitioning plus k, where k is the number of switches in that partition, k log L over k, and k log n plus k. So to get a feel for what this bound is, we can think about this bound as kind of information theoretically describing that sequence of experts, i.e. we had to name the first expert. That cost us log n bits. Each time we switched, we had to name the one we switched to. There's n minus 1 things we switched k times, so that cost another k log n minus 1 bits. Then we have to name where these partition points are. Well, roughly, if you're switching k times, each thing in a sequence of length L is roughly L divided by k in length, and so to name the first number is roughly something that's going to take log L over k bits, and then you think about the next offset, and there's k such of those offsets. So this is kind of we can kind of understand the bound as thinking of it in bits. And we get the smooth dependence on size. If L was very large, well then L times log n minus 1 is vacuous, so we're not somehow doing magic. Okay? But if L is small, then we have a reason. I mean, if k is not too large, we have a non-vacuous bound. Okay. Questions so far? So, I'm not going to prove this bound, but I'll sketch the idea of how we can prove it. Okay. Many of you are taking graphical models or unsupervised learning and are kind of used to these probabilistic models. So one way to think about what's going on, I'm not going to have a proof here. But this efficient algorithm actually exactly simulates a less efficient, expensive algorithm. Not this algorithm which we showed before, but another algorithm. Now imagine if we have a sequence of length L, and we have n potential experts. There's some n to the L potential sequences. So our set of experts has cardinality n to the L. Okay, we can imagine this, all possible labelings of a sequence. Now, rather than assigning weights to these sequences uniformly, we assign weights to these sequences in accordance to how often they switch. Okay, so what's the given weight or probability that will associate with a given sequence? So the probability of a given sequence will equal well, 1 over n for getting the first expert. Every time we're going to switch a certain number of times, we're going to switch k times, so the probability of switching on any given trial is alpha over n minus 1. Now, the probability of switching is alpha, but then switching to a particular expert, there's n minus 1 other experts we potentially switch to, so we'll associate a probability of switching to a particular expert. We'll do that k times, and then we'll stay with the same expert, 1 minus alpha L minus k choose times. So if we look at some particular sequence of experts, the probability which we'll associate with that sequence of experts is just 1 over n, the initial number of experts, alpha over n minus 1, the number of times we switch, 1 minus alpha L minus k, the number of times we don't switch. So that gives us a non-uniform distribution over these n to the L experts. Then if I was doing more than waving my hands, I wanted to do a full proof, what I would then prove for you that if I went ahead and I ran the expert algorithms with these n to the L experts, each of these n to the L meta experts with this initial weight, then that algorithm is exactly simulated by this. But I'm not going to prove that for you. It's similar to our simpler algorithm that we described, where we created uniformly weighted things that we couldn't run efficiently. Now we'll have non-uniformly weighted things that run efficiently and are simulated by this. Which then, if we think about it in terms of creating a bound, by choosing alpha equal to the switching rate, it's not surprising that this is the optimal parameter which we should set alpha to. So one can give an algorithm, one can prove an upper bound for it. One might be curious, is this really necessary? Is there any benefit in practice? There's lots of real experiments with this algorithm, but I have a simple simulation experiment to show you what happens. So I set up the following simulation. We have some 800 trials. We have 3 shifts between experts, 3 shifts. Our number of experts is 64. Use the square loss. I chose the optimal parameter for alpha. And then when I set up, a typical expert would have expected loss of 1/12 per trial, and a random expert would have loss 1 over 1/20th. I did this, I can't remember exactly how I achieved that. And we can then look and see the performance of these algorithms. So let me explain the details of the performance here. So what I'm plotting here is the total loss over time. Here I'm plotting trials. So our loss is accumulating over time. So I had one best expert between trials 0 to 200, another one from 0 to 400, another from 0 to 600, another from 0 to 800. So the very best we could possibly do, so if we did roughly the loss of the best sequence of experts would be this. We chose some random expert. Well, we looked at how it did. It's making this loss 1/12 per trial, so it's roughly 800 times 1/12. This is 800 times 1 over 1/20th. So somehow we expect our algorithms to be bounded in here. So then what do I continue to plot? So here, what I'm plotting is suppose I plot the loss of an arbitrary, this line here represents the loss of not adding in this share update. If I now add in the share update, so without the share update, I just do the loss update. I do quite well for the first 200 trials, and then I somehow don't figure out what's going on. The exponential weighting doesn't work out. Whereas if we do the sharing, there's the 2 variants roughly. All algorithms do the same up to 200, but then it begins to track the rate of the best expert. So whenever we change segments, the algorithm is initially confused, but then it rapidly tracks. so we can understand what's happening. So to understand what's happening, I've plotted the weights of the two algorithms. So here's the algorithm without doing the share update. And we see it rapidly figures out this is the weight of experts. So I have some 64 lines here. Really, you can only kind of see one line at a time because one line goes up, the other lines rapidly go to 0. But the weight corresponding to the best expert rapidly approaches 1. Then once it makes it to 1, the weight's quite high, and somehow it has to unlearn that weight to learn a new weight, but it doesn't start unlearning that weight until it's almost time for it to shift again, and it remains confused, and it never adapts because it can't unlearn the previous fast enough with the sharing does. So when you share, you see you don't quite figure out the best expert to the same degree as you did at first one, so you pay a little bit more loss per trial, but then it's able to adapt rapidly. Okay, there's been a variety of experiments. This is the rest of the notes for the online lecture. Massey takes over next week. And that's it. Any questions? Okay. For those of you who are taking research methods, I believe the coursework has been, Massey's posted a coursework to Moodle. There'll only be one coursework by that.